Thank you everyone for joining us in this STRIDE webinar. Our today's topic is assessing and addressing deficiencies in the HCM weaving segment analysis phase 2. So good afternoon to everyone. My name is Ishtiak Ahmed, and with me I have the PI and the co-PI of this project, Dr. Nagi Rafael, Dr. Lily Eleftheriou, and researcher Dr. Ehsan Amini. Right. Go to the next slide. So this is today's presentation's outline. So I'll start with the introduction and background of this project. Then we'll see the primary objectives of this project. Then I will talk about the proposed speed and capacity models that we have developed for weaving segments, followed by the data acquisition and processing needed in this project. Then I will hand it over to Ehsan to talk about the results from the model development and evaluation and sensitivity test, followed by, at the end, the main summary and conclusion of this project. So this project is mainly about freeway weaving segments, which are known as one of the critical components on any freeway corridors. The reason being, they are often, in most cases, followed by, it starts with an on-ramp and they have an auxiliary lane and followed by an off-ramp. What happened in these cases, if the segment is short enough and the traffic demand is high, we see intensive lane changes in those weaving segments during peak hours, and that creates a lot of turbulence on the traffic, so the operation can degrade, and that can also affect the traffic safety. So there is no doubt that the operational analysis of freeway weaving segments is really important. Any bias and error involved in the analysis models and the procedures can impact the facility-wide and reliability analysis as well. However, the task is challenging, not only because there are a lot of things going on in a weaving segment, including driving lane changing behavior, abrupt lane changing, and the whole complex scenario of traffic flow, but also because it's really difficult to collect the data from all the origin destination routes going in and out of a weaving segment. So it's really a challenging task. However, the Highway Capacity Manual, HCM, since 1950 have been developing freeway weaving segment analysis procedures, which had been widely used by many traffic agencies. So a brief history about the weaving analysis procedure in the HCM is listed here. So the procedure was first introduced in 1950 HCM, then a revision in 1985, and a major update on the weaving segment analysis procedure in the HCM 2010. That method is still used to date in the latest HCM, which is the HCM 7. So the HCM distinguishes all the weaving segments that are one-sided. That means like both the on-ramp and the off-ramps are on the right-hand side of the road, into two major categories. One is called the ramp weaves or the type A weaves, and the other one is called the major weaves, which are further subcategorized into type B and C weaves. So we will talk about these two types of weaves more detail in the later part of the presentation. So a bit more background of this project is this project was mainly motivated by some of the limitations that came into light recently about the HCM weaving segment analysis method. So the HCM method for estimating the speed and capacity of a weaving segments depends on several steps, and each step has different models, like separate models for lane change prediction and separate models for weaving and non-weaving speed. And different models and separate models means there are like more chances of uncertainty and modeling error. So the process was overall a bit complex. Recently, it was found that the HCM estimated speed is not sensitive enough to different critical parameters, such as the segment length. And there is also a tendency of overestimating the density. The HCM method often predicts the weaving segment speed to be higher than the non-weaving segment speed, or non-weaving vehicle speed, which is sort of counterintuitive because one would assume that the non-weaving speed would be higher because they're not involved with much lane-changing maneuvers compared to the weaving vehicles. Also, when estimating the capacity, the flow rate at capacity does not follow the relationship of the fundamental traffic flow and density, speed and density. So that is another issue. And also the method, the HCM method, was primarily developed based on the research done under the NCHRP 375 project. And in that project, most field data came from major weaves. So when we are talking about the different kinds of weaves, there was some undersampling from ramp weaves. All right. So these limitations motivated our team to develop to lead the phase 1 of this project. And in phase 1, the team proposed a novel and simplified speed and capacity model for type A or ramp weaves only. So the main focus was on ramp weaves. And it had some strengths and limitations. For example, the proposed method models were simple and intuitive, and it actually leveraged the fundamental traffic flow equation to estimate the capacity. The project collected data from 15 ramp weave sites. So there are enough variations of sites in that project, and the speed and capacity estimates were found to be sensitive to the critical parameters. When compared to the HCM model results, it was found for those sites, the model development RMSE was significantly lower for the proposed model, proposed speed model compared to the HCM model. Although given that like many of the sites were included in that NCHRP project, so that was a significant improvement that came out of this project. However, the proposed speed model did not include in the phase 1 model, did not include any lane change configuration parameters. And as I said, I'll talk about the different types of weave later. Those are mostly classified based on how many lane changes the weaving vehicles would need to make to go from either ramp to the freeway or freeway to the ramp. And because of that, that model form was not applicable to the other type of weaves, such as the major type B and type C weaves. The second limitation was that the capacity model proposed in that phase 1, it relied on a big assumption that when we are observing or when we are collecting the data, that observed weaving flow rates, the ramp to freeway and the freeway to ramp flow rates remain the same between the observed condition and capacity condition. Now, in phase 2, our main objectives are to eradicate those limitations that we had in the phase 1 of this project. To state the objective, there are 3 main objectives: to develop a speed model form that is applicable to all type of waves, regardless of their lane change configuration type; to reassess and improve the capacity model proposed in phase 1; and to compare the model performance against the current HCM7 weaving segment model. All right. So far, I discussed the 2 types of weaves, ramp and weaves, where ramp and major weaves, where the major weaves can be subcategorized into 2 further types like type B and C. In total, we can say there are 3 types of weaves. And in this figure, I'm explaining the main difference of these 3 types of weaves. So let's say we have the weaving vehicle or the weaving routes indicated by the diagonal arrows, and the non-weaving routes, which are the freeway to freeway and ramp to ramp, shown by the horizontal arrows. So the classification is mostly based on the lane change requirement by the diagonal arrows. So if any of the weaving vehicles or the weaving routes, like the ramp to freeway and freeway to ramp, they have to make 1 lane change each, or that's the minimum number of lane changes required to make those maneuver, then we call that type A weaves. So the phase 1 was about only that type of weaving segments. Depending on the minimum lane change requirement, we can have 2 other types, which is type B and type C. So if the minimum lane change requirement for any of the 2 weaving maneuvers is 0 or 1, then we call that type B. If it is for any of the maneuvers, then we call that type C weaves. So in this project, we tried to incorporate the these lane change parameters to make into the speed model and capacity model to make the model form applicable to all three types of waves that you are seeing here. Okay. So let's talk about those lane change parameters and see some sketches of like what they look like. All right. So these lane change parameters, as I said, are important because the turbulence that we see in the weaving segments are created mostly by the lane changing activities. And in many times we see that the mandatory lane change, which are in the HCM called as the minimum lane change required by weaving vehicles, they are the predominant type of lane changes in a weaving segment, listed as LC sub RF. RF stands for ramp to freeway, and LC sub FR, FR stands for freeway to ramp. In addition to these two, HCM also uses another parameter, which is called N sub WL, or stands for number of lanes from which a weaving maneuver can be completed with a less than or equal to one lane change. So if you think lane changing as kind of a load on traffic operation, also on the driving task, LCRF and LCFR, higher these numbers, the more that load is. And if you think like having more options, so that is kind of represents a comfort in driving maneuvers. N sub WL represents that, and higher that number, that means the drivers have more option and they require less number of or fewer number of lane changes. In this project, in the proposed speed and capacity model, for the phase one model, we actually did not need to use these parameters. The reason for ramp weaves, those numbers are fixed. It's one lane change required for ramp to freeway and one lane change required for freeway to ramp vehicles. Now that we are trying to incorporate or like make those models applicable to other type of weaves, so that's why these parameters are becoming more important. In addition, we are distinguishing these parameters N sub WL that is currently used in HCM between N sub W for ramp to freeway and N sub W for freeway to ramp, just to represent or to reflect the difference in difficulties or the comfort of lane changing maneuvers between the ramp to freeway and freeway to ramp vehicles. So in these two figures in the bottom, I'm showing some examples of how do the lane change parameters look like. So let's say in the top weaving segment, we have a shared lane which can be used by both the freeway by both the traffic from freeway to ramp and freeway to freeway. So that actually is helping to reduce the LC sub FR to go to 0 and NWRF or NWFR to go up. So there are actually two lanes from which a freeway to ramp maneuver can be completed because of that shared lane. On the other hand, the lane change requirement for the freeway to ramp vehicles is now going down. For in the bottom figure, that's the type C weaves because we have two lane change required for the ramp to freeway vehicles. So now it's actually like a bit more difficult for ramp to freeway vehicles to make that maneuver compared to the freeway to ramp vehicles because they have a lot more lanes from which they can complete the weaving maneuvers with no lane changes. So for this reason, these two parameters are really important to reflect the difficulties and the easiness of the ramp to freeway and the freeway to ramp vehicles to complete the weaving maneuvers. And that should also be reflected in the estimated speed because the speed model takes into account the total flow rate and the load imposed by the ramp to freeway and the freeway to ramp vehicles on the traffic operations. So we'll talk about that in the next slide. In the phase one, we developed this weaving segment speed model that is based on the assumption that the weaving segment speed should be less than an equivalent basic segment speed. Now, what's an equivalent basic segment speed? So basic segment, the term we borrowed from, that's the term we borrowed from HCM. So basic segment does not have any on-ramp and off-ramp within that segment. And because weaving segment has some off-ramp and extra lane changing maneuvers, so that speed S sub O for the weaving segment should be the basic segment speed minus an impedance induced by those lane changing maneuvers and the weaving flow rates. All right. So that is the basic form of the speed model for weaving segment. Now, how to estimate this SIW? So we tested several model forms where we included the ramp to freeway flow rates, the freeway to ramp flow rates, and we also tried to see the impact of the total flow rate as well as the weaving segment length, which is really important because shorter the length, you have a more concentrated turbulence. So we came up with this final model form upon trying a few other forms. And as you can see, we have also some modeling coefficients, which are represented as the alpha, gamma, and the delta parameters. And at the end, we applied this model form to our ramp weave data and fitted this model and estimated these alpha values and gamma and delta values. We used kind of the basic model form in phase 2 when we tried to develop a universal model or kind of a model for all kind of weaving segments. But we introduced these lane change parameters to reflect the weight or the load imposed by the ramp to freeway and the freeway to ramp vehicles using this equation. All right, so we kept the basic model form same. Like you can see that we still have the total lane change, total number of lanes, the flow rate, and the segment length. But definitely, because of these changes that we are making here, we need to recalibrate or we need to re-estimate the coefficient values using data from both major and ramp weaves, like all three types of weave, A, B, and C, and to estimate these coefficient values. Now, what are the main changes here, or what is the difference between the previous and the other one? This one is accounting for now the potential influence of lane configuration parameters. And the example that I showed you, like through exit and exclusive exit lengths, like shared and exclusive exit lengths, it can now capture the effect of those different lane configuration parameters. And that actually makes this model form applicable to all type of waves. So these are all about the speed model. Before I show you the results on the speed model, let's talk about what was the issue with the capacity model. So in the phase 1, the way we estimated the capacity was that, okay, so we have the basic speed model, but instead of thinking about the current observed flow rate, if we think about the flow rate at capacity, that speed model has now become a quadratic function of capacity, because the basic segment speed model is a quadratic function of the flow rate. Now at capacity, you have the capacity flow rate as the flow rate. And the SIW equation, it's only a function of the capacity. All right. So in this equation, we have this unknown C sub W, which is the capacity that we want to estimate. And based on the traffic flow fundamental equation, we can say that the speed at capacity can be written as the ratio of the flow rate and the density at capacity. So in the bottom equation, we have actually two unknowns. The other unknown here is this density at capacity. HCM suggests that the density at capacity is 43 passenger car per mile per lane. Now, if we take that as ground truth, then we actually have only one unknown, which is the capacity. And once we plug in the coefficient values, this equation can be reduced to a quadratic equation like this. And the only unknown here is the capacity, and it's analytically solvable. That's the method that we use in phase 1 of this project. However, the main assumption here is that the observed ramp to flow rate remain the same. Let me go back a few slides. So we are not touching these two or changing these two when we are converting that equation to this one, and we are talking about capacity. And that is a big assumption. So in this project, we tested an alternative form or an alternative, more realistic assumption, which is it's not the weaving volume that remains the same, rather it's the weaving ratio that remains the same between the observed condition and condition at capacity. So what is that weaving ratio? The weaving ratio, I mean, it's the ratio of the weaving flow rate to the total flow rate. And we are assuming that we should multiply that flow rates by a factor, the factor which is the same factor or the same ratio between the capacity and the observed flow rate. let's assume that that multiplying factor is mu. So we can have the observed flow rate should be multiplied by mu to estimate the weaving flow rates at capacity, as shown by this equation. So that actually reduces the problem down to, instead of estimating capacity, we need to estimate the mu, or the multiplying factor, because it gets multiplied to both the observed total flow rate and the observed two weaving flow rates. Okay. So if we consider that, the speed at capacity equation now becomes a function of mu and mu square for the basic segment speed. And in the SIW, it now becomes a function of expansion of mu to the power gamma, because gamma was used as an exponent. Now that makes, I mean, of course, that's a more realistic assumption, but that makes the problem not being like, it's not solvable analytically. This equation still can be solved through an iterative method. And we tried both methods and we tested both assumptions. At the end, another finding that we should mention here is that for most cases, the difference between these two methods, the method that is based on that we developed in the phase one and this more realistic assumption, in most cases, they kind of yielded the same capacity values. However, if the observed volume or the observed flow rates are really low, only at that time we see a significant difference between these two estimates. All right, so we'll see results from both. Now let's talk about the unknown or the HCM prescribed value of 43 passenger car mile per lane, because that's another improvement, or that's another change that we made in the capacity model. So in phase one, we took that as the recommended value, but when we looked at the field data from the NCHRP 72016, who are currently working on developing new methods or improved models for HCM on-ramp or ramp, diverge, merge, and weaving segments. It's their courtesy that they gave us the data and also looked at what is actually the field value of density at capacity. So this diagram is coming from the NCHRP 07-2016, and they collected data from different types of weaving and merge and diverge segment. You can see here collector distributor weave, and we have complex weave, which is also another name for major weave. And they also have data from merge and diverge segments. In general, what's the observation? Or the left-hand side axis, the left-hand side vertical axis is showing the density at capacity for these segments. And the right-hand side vertical axis is showing how many sites they use to get those numbers. All right. Surprisingly, in all these cases, those values are actually much lower than 43 passenger car per mile per lane. Particularly if you see the weaving segments, which is here, CD weave and complex weave, those are close to 35, even sometimes lower than that. All right. So these observations actually kind of suggested us that like we should reconsider this critical value, critical density value. And at the end, we decided that 35 passenger car per mile per lane is more realistic and it matches more closely with the field observation. All right. So that's the final change that we made to the capacity model. Now, in order to develop this speed model and to estimate the coefficients and consequently estimate the capacity model, we needed a lot of data, both from type A, type B, and type C weaves. So we relied on the phase one sites for the type A weaves. So we had 15 type A weaves from that phase. And for this phase, we collected loop detector data from 14 type B weaves located in Utah and California. Many of those data came from PEMS. And then we also used our drone technology and camera to collect data from 6 type C weaves in Raleigh. So for the loop detector data, as you understand that at the end, we needed the origin destination based flow rates, like weaving flow rates. For the loop detector data, we used a method to estimate those flow rates. It's called the proportional weaving assumption. And for the drone data, we actually used both drone and ground cameras as shown by this figure here. So the two ramps were covered by the two ground cameras, and the drone covered the total entry flow rate and the on-ramp flow rate. At the end, it was kind of a mixture of automated and manual data extraction. So from the ramp videos, we match the vehicle color and the number plates to estimate the ramp to ramp flow rates. That ended up like being a useful parameter in estimating the weaving flow rates, because we have the total flow rates from the drone. So we can subtract the ramp to ramp flow rates from the total flow rates to estimate the remaining ones, such as the freeway to freeway, freeway to ramp, and ramp to freeway flow rates, right? From the raw data, we found that there are some issues with the raw data, particularly with the loop detector data, because there's always a chance of including mixed state observation and inconsistent data point. So in this diagram, I'm showing some examples of mixed state. So when we aggregate the loop detector data, there is a chance that part of the data is coming from free flow condition, and part of the data, or part of that 5-minute period, was probably in a congested condition. So the average data point kind of ends up in a place where it actually doesn't go or doesn't match with the fundamental traffic flow or shape of the speed flow diagram. So here I'm showing an example speed flow diagram. As you can see, these data points are kind of representation of those mixed state and inconsistent data points. So we used a previously established method for removing those data and to clean up to have steady state traffic observations. At the end, this is our final data distribution. We aggregated all the data in 5 minutes interval. From ramp weaves, we have more than 11,000 data points. From type B weaves, we have more than 19,000 data points. And for type C weaves, because of the limitation of drone data flight time, we didn't have as much data point as the other types. So it was 106 data points. So as you can see, type B and C, which consist of the which compose the major weave types. So those in that weave type, we have like a much higher representation of type B weaves. And this is also attributed to the fact that type C weaves are mostly seen at system interchanges. So those are not as common as type B and type A weaves. At the end, we developed two models using the same model form, one for type A and the other one for type B plus C weaves, just to account for some unobserved variation between these two, the ramp and major weaves. So for this slide and for the remaining ones, I would like to hand over the presentation to Ehsan. Ehsan, you can start.
Okay, sure. Hello, everyone. It's Ehsan Amini, and I'm postdoc researcher at University of Florida. And I had the chance to work on this project with Dr. Lily, Dr. Nagi, and Dr. Ishtiak. So to calibrate the model, we separate the database into two parts, 15% and 85% each. And we kind of randomly did that. Ishtiak, next. Yeah. And we tried to minimize the value of RMSE, root mean square error, between the observed speed and predicted speed. The formula for RMSE is here, which N is number of data points that we have, Y is the observed speed, and Y bar is the predicted speed that our model will predict that. After that, we try to minimize the value of RMSE, and we kind of try to estimate these coefficient values, alpha, gamma, theta, and theta. We set some constraint on this coefficient, which was this coefficient, like the constraint was that this coefficient should be between 0.2 and 20. We ended up getting these values by doing try and error on the calibration part, and we tried to keep this coefficient in a reasonable range. So and we don't increase the value of RMSE in the model prediction. And we can go to the the value of, as you see here, the value of RMSE for the ramp weave was 2.6 3, and for the major weave it was 3.4. Can we go to next slide? So we did calculate the value of RMSE based on the evaluation data set as well, which you can see these values here. Oh, sorry. Here, this, yeah. So as you see, these values for calibration data set and evaluation data set were pretty close to each other, which means our model didn't get overfit on the calibration data set, and we kind of proved that our model can predict the speed in a good way. We go to the next slide. And here we plotted two graphs. The left one is for type A, the right one is for type B and C. And here we have predicted speed in a vertical line versus observed speed in a horizontal line, horizontal axis. And you can see here for both graphs, the predicted speed is pretty much similar to observed speed in the field, but in type B and C, we observed some regime here that our model kind of predicted the speed is like more than what we had in the field, and it mostly was when the observed speed. It was mostly when the observed speed was between 40 and 50, and we found no geometrical reason for this observation, but we don't know. I mean, the guess that we have is like maybe these data points are related to oversaturated data, oversaturated condition, and we couldn't remove that during the data cleaning. If we can go to next slide. Here we have average speed versus flow rate for type A, again in the left side, and type B and C in the right side. And as you see, can you, yeah, as you see, and Ishtiak mentioned before, when the flow rate is less than 500 passenger car per hour per lane, yeah, the speed in the observed speed is pretty much similar to free flow speed in the section, and after that point we see drop in the speed due to turbulence in weaving area. And here again you can see that we have those data points that the observed speed, which are these blue dots, are not pretty much close to those data points. And as you see, they are probably in the congested condition. Yeah, but we have those data points here as well. If you go to next slide, sure. Yep, we did some sensitivity analysis on the capacity model. Here we have capacity versus length of section. And we kept all the parameters and in the model like consistent, and just changed the length of weaving section. And as you see here, we have HCM prediction for the capacity, and as we can see here, HCM has like very linear relationship between the length and capacity of weaving section, while the capacity that our model predicted is like more sensitive at the very beginning of the section. So if we have like at a very short section, sorry. So if we have a weaving section, like for short weaving section, increasing the length will increase the capacity more than when we have like long weaving section. Can you go to next slide? So yeah, here we have capacity versus weaving ratio. Again, both HCM and our proposed model they have like the same relationship between these two. But yeah, again, as you see, the predicted capacity for models is less than what HCM is calculating. Can we go to next? Oh, next slide, please. Yeah.
Mhm.
Here we have capacity versus number of lane in the weaving sections. The red line here at the top is the HCM prediction, and you see we have HCM has like no sensitivity to number of lane in the weaving area. But in our model, by increasing the number of lane, the capacity of weaving section will increase too. Can we go to next? Thank you. So here we have a summary and conclusion about this presentation. At the very beginning, the objective of this project was to estimate the average speed and capacity in weaving area. We didn't define, we used two different parameters to capture all geometric feature of the weaving area. These parameters were minimum number of lane changing required for the ramp to freeway movement and freeway to ramp movement, and the number of lanes from which a weaving section can be completed with 1 or 0 lane changes. Yeah, so the model that we recommended uses the equivalent basic freeway segment, and we just try to capture the effect of turbulence that happen based on because of the weaving area. And can we go to next? And the model was in the modeling we ensured that the models are consistent between with the basic freeway segment, and we don't need to like calculate the number of lane changes and estimate the weaving and non-weaving flows speed, which based on HCM we should do that. And these models are pretty easy to calibrate it based on the field data. And yeah, we found that the model can be fitted very well on the data set database. Yeah, as Ishtiak mentioned, the highest observed density that the highest density at capacity that we observed was 35 passenger car per mile per lane, and beyond that we had congested condition. The proposed model was more sensitive to length of weaving section, number of lane, and weaving ratio than HCM, and we used the same. Yeah, the NCHRP 726 project used the same model form, and they try to recalibrate that. I think Dr. Nagy can help us to provide like more information on that project if you want to jump in, Dr. Nagy.
Can you hear me?
Yes.
Yes, thank you, Ehsan. This is, I did want to make that point here is that our project, the STRIDE project, was going on in parallel with 726, although our project was a little bit behind in terms of the data collection. So what has happened is we are working, and I think that's a good example of collaboration between a national research project, NCHRP 726, and the STRIDE project to try to combine both data sets and improve even more and make the model more generic for a larger number of sites. So that work is ongoing. We are sharing the data, and one of the things that is very consistent is what Ehsan said, the model form has not changed. So the only thing we're doing is, or we will be doing, is to recalibrate the model based on a much larger data set that would hopefully give us a little bit more confidence in the values. Although so far, based on both the work that 726 did and the work we've done here, the model form seems to be a lot better. And just one last thing, I do want to emphasize what Ishtiak has mentioned in terms of the capacity model, and that is we still will propose to use the quadratic equation in cases where the volumes are very low. The V over C doesn't seem to be a problem. It's only when we get to high V over C that we may be concerned. But in those cases, as Ehsan has shown, the two models are very close to each other. So I would think that also both the capacity and the speed model will make it much easier for the practitioner to quickly evaluate those different places.
Thank you. And the recommendation for future research is, first we saw that based on sensor data, we can collect like lots of data points, but sometimes it's pretty hard to capture the breakdown and see if we have the breakdown or it's like due to any other, and if we have like any congestion due to any other issue, such as like a weather situation or crashes. It's kind of not possible to filter those data. And we suggest that we have, for future research, we should have like a balanced number of data for different traffic state in the database. And the last one, again, although in this research we treated the density at breakpoint to be like consistent, and it was like 35 passenger car per mile per lane. We found that based on the field data, we found that this number can be varied something between 22 to 35. So we can like use it as a variable or in the next like research. Thank you.
All right, thank you, Ehsan. You can put your questions in the Q&A session, and we will go through this. And we also have, we'll also give you a server link. We'll give you a server link in the chat box. Thank you.
Thank you very much, Ehsan and Ishtiak. And be happy, either the presenter or myself or Lily will be happy to answer any questions you may have.
So let me state the questions that we have received. So we have received two questions so far. Dr. Johammer is asking, how did the new model compare to the HCM model for error on the collected data sets?
The error, well, on the phase one case, the error was about 1/3. The speed error was about 1/3 of what we got in the HCM. It's also very consistent with what Ishtiak mentioned, that the HCM tend to overestimate density, which means it's underestimating the speeds. These are the type of error we're seeing, which we feel anything that is below 5 miles per hour is a reasonable estimation for a macroscopic model. And the other thing I also want to mention has to do with the fact that the configuration, our motivation for the configuration parameters, part of this came out of a evaluation of the model forms in 726. They actually did a little workshop and have some folks from different DOTs to evaluate the model. It was well received, but there was some issues about including some additional configuration parameters, and that's what the model does. And then finally, one of the things that maybe was not mentioned here, only in passing, is how the heck do you get weaving and non-weaving flows with sensor data? And the research here actually developed and validated a method so that only with volume data on the ramps and on the main line, you can estimate those weaving volume with a reasonable degree of accuracy.
Yeah, on that, I'd just like to add that because of time limitation, we couldn't present the results on the proportional weaving assumption method that I mentioned. So, but we have that in the report. And if you want to know more about that method that only requires the entry and the end flow rates on the freeway and on-ramp and off-ramp, we'll be definitely happy to help you and demonstrate how that method is working. It's working great. Let me go to the second question again from Dr. Hammer. Do you have an available spreadsheet version of the new model that is usable by our practitioners? And I think, Nagy, the answer is yes. You created a spreadsheet?
Yeah, although I would advise Joe, if he can wait about 6 weeks or so, we are going to recalibrate the model, including some of the 726 sites. So I would suggest that that spreadsheet would be available and updated early next year. We definitely are going to be presenting on this work at TRB.
All right, yeah, thanks. Let me go to the third one. It's coming from Mr. Werner Brilliant. When will the final report be published? So,
good question. Is it published or not?
No, so we are right now addressing the comments that we received from the reviewers. We got very good comments from them, and currently the timeline looks like we should be able to address those comments very soon, and then it will go back to the reviewers, and then Stride will process the whole thing, and then it will be published after that. Yeah.
So again, early next year, more likely.
More likely, yes. So comment from Dr. Hammer, sure, I have waited about 40 years, so another 6 weeks is okay. Yes, thank you.
Thanks, Joe.
Any other questions or comments?
If not, then we'll hand it to Ondine.
We have
good.
one from Shen Dong. Thank you, Shen. If the highest observed density is about 35 passenger car per mile per lane for both types of weaves, does it mean density at capacity for the new weaving method will be around 35 instead of 45? If it's that, K sub C for oversaturated method at chapter 25 is a global variable for all segment types and 45, I guess, 45 passenger car per mile per lane. Could you please advise any suggestion to handle such inconsistency? That's a great question, Shen. So just to tell you one thing, for the HCM segment analysis, for weaving segment analysis, the current value is not 45, it is 43 passenger car per mile per lane. And the answer to your first question is that yes, the density at capacity for the new weaving method will be 35 passenger car per mile per lane. Now, concerning your second question, the oversaturated method at chapter 25 use K sub C as a global variable, and that is 45 for all segment types. I'd like to hear from Nagy or Lily or Ehsan about that, the oversaturated method, which I think is the facility-wide analysis. So if that uses 45 as a global variable for all segment types, what is the implication of our new findings on that?
Yeah, that's a tough question. I mean, and I'm also let Lily maybe chime in if she can. The reality is basic freeway segment honestly never break down on their own. Typically, what causes a problem on basic freeway segment is usually some kind of on-ramp or off-ramp. If you have looked at, and Ishtiak, maybe you want to go back to that slide from 726, because that's not just weaving, by the way. And as you could see here, these are various types of on-ramp, off-ramp, merge, diverge, obviously no basic segment. My sense here is this going to have to be a capacity committee decision based on the 726 research. We can only talk about what we have seen on the weave, but if you can see here on all these merges and diversion, and these were actually measured in a pre-breakdown mode using the definition in the HCM. So all of these density were associated with pre-breakdown flow rates. So it's likely down the road that those density may have to be revised. Lily, do you want to add anything?
I think.
I don't think Lily was able to make the meeting today.
Oh, okay. I'm sorry. I was not aware.
Okay. About that, I'd like to add one thing, is that I think it's a question for the committee members who are involved in the HCM 2010, because that's a question for them as well, because weaving segment K sub C, or the density at capacity, was 43. But for the facility-wide or the oversaturated method, it was 45 for all types. So why there was still a discrepancy of 2 passenger car per mile per lane, and how did they address that issue at that time? So I think that's a question for them as well. All right, but that's a great question, Shen. Thank you. Any other question?
Okay, so Undine, anything on your end you want to wrap this up?
No, I would like to thank you all very much for this great presentation with really important work and for sharing it. We will provide a recording and it'll be available on YouTube and the STRIDE website within the next week.
Very good.
That's
Thank
good.
you all. Thank you for.
Thank you.
Thank you.
Bye.
Goodbye.